Alright, let's do another example of finding the derivative using the difference quotient. This time our function is x squared plus 3, which differs from the last example only by that constant 3. So let's see what kind of effect that has. Here's our difference quotient in blue. And now we'll just go ahead and plug into this. Remember, we're going to plug x plus h into our function wherever x is, and also x itself. So we end up with the starting difference quotient, f prime of x is equal to the limit as h goes to 0 of x plus h squared plus 3. And then we subtract the function itself, x squared plus 3. Remember to use these brackets because that negative sign needs to distribute amongst both of those terms. So we have the limit as h goes to 0, and now we'll just expand that first binomial, x squared plus 2hx plus h squared, plus that 3, and then we have minus x squared and minus 3 all over h. Now we can do some cancellation, and what we'll notice is that both of these x squareds go away, but so do these constants. And so what we realize here is that the constant really didn't matter at all. And hopefully you'll see how that makes some sense once we plot these graphs. So now here's our simplified limit. We just have 2h plus h squared all over h. And we notice that every element of that has an h in it, so we can knock some of those h's out. Number divided by itself is 1. And so we end up with the limit of 2x plus h, just like we did in the last example, and as h goes to 0, that's just 2x. So this is really the same derivative as f of x equals x squared, so you see that that constant doesn't matter. So let's graph these and see if we can figure out why that is. The graph of x squared plus 3 is just the regular parabola x squared elevated by 3 units, and it has a positive and increasing slope on the right side of the y-axis and a negative and decreasing slope on the left side of the y-axis, and sometimes I refer to that as increasing in the negative direction. And our derivative is just 2x, which is just a line. And you can see that it captures all of the features of the slope of the function. In other words, it doesn't really matter if we raise or lower the function f of x equals x squared. That doesn't have any effect on its slope. And so it's easy to see why the derivative of that function plus or minus a constant will be the same as just the derivative of x squared.